So this is ELC 131, Circuit Analysis 1, and we're going to talk now about electromagnetic induction. And electromagnetic induction is when we have relative motion between flux and a conductor, and that induces a voltage in the conductor. Now, you saw an example of electromagnetic induction earlier this semester in the Sources of Electricity video, where I connected a galvanometer to a coil of wire and moved a permanent magnet towards the coil and away from the coil. And as that permanent magnet moved towards the coil, the galvanometer deflected in one direction, and as I moved the permanent magnet away from the coil, the galvanometer moved in the opposite direction. And you hopefully noticed in that video that the galvanometer deflected only during the period of time when the permanent magnet was moving, that a stationary magnet had no effect on the galvanometer or did not generate any current. So let's take a look at what's going on here. So we see a magnetic field that's developed between the north and south poles of two magnets. And what we're going to do, or what I'm going to do, is I'm going to take a conductor, and I draw this conductor somewhat at an orthogonal view, so we're not looking at just the end of it. And this, excuse me, and I'm going to move this conductor up through this magnetic field. Now, let's review for just a moment. In the last video, we talked about how if I have current flowing through a conductor, around that conductor will be a magnetic field. And the direction of that magnetic field, of course, is determined by the direction of current. So if moving electrons in a conductor makes a magnetic field, moving a conductor through a magnetic field has to make electrons move. I can't have it one way and not have it the other way. If moving electrons through a conductor makes flux, moving a conductor through flux has to make electrons move. Now, we've got another right-hand rule for everybody, and we use this for conventional current flow. But what you do is point the index finger of your right hand in the direction of flux. Your thumb points in the direction of motion through that flux. And your second finger, held perpendicular to the other two, shows you the direction of current. So if flux is going this way and motion's going up, current's flowing from you towards the whiteboard. So current in this conductor would be flowing in this direction. Therefore, the induced voltage would have a polarity of positive to negative. Now, if I move this conductor back down through the flux is still going this way. Motion's now going down. Current will be flowing from the board towards you. So the polarity of the voltage and the direction of current would be reversed. Now, the terminology we used here, or I used, is that there's relative motion between flux and the conductor. And what this means is it doesn't matter if the flux is stationary and the conductor moves, or if the conductor is stationary and the flux moves. as long as there's relative motion between these two. Now, there's five factors that determine the magnitude of this, or not the magnitude, but affect this induced voltage. And they are the flux density. The stronger the field, the greater the induced voltage. The second is the direction of flux. And again, we saw that with the right-hand rule. Flux is going this way. The third, of course, is direction of motion. Again, our right-hand rule, flux is this way, motion's up, current flows from you to the board. If flux is this way and motion's down, currents from the board towards you. And also the rate of motion. The faster the relative motion between flux and the conductor, the greater the induced voltage. So the faster I move this conductor, the larger the voltage will be that's induced. And the fifth factor that affects this induced voltage is the angle between the flux and the conductor. And mathematically, this says that the induced voltage, and again, note I write this as a lowercase cursive v to symbolize that this is an instantaneous voltage, equals the maximum voltage that can be induced times the sine of the angle, that says psi, the sine of the angle between the motion and the flux. So let's look at another situation. And what I'm going to do is take a conductor and I'm going to rotate it through this flux. Now, again, imagine this is my conductor and I'm going to rotate it around in this flux. Now, at this first point up here, the angle between the motion and the flux is 0 degrees. And V max times the sine of 0 degrees equals 0 volts. So at point number 1, I've got 0 volts. Now, as I move around this circle to point number 2, let's just say that the angle that exists here is 45 degrees. And V max times the sine of 45 degrees equals V max times 0.7, times the sine of 45 degrees equals 0.707. So at 45 degrees through our rotation, point 2, I will have a voltage of the maximum times 0.707. And as I move around the circle to this point, where the angle between the flux and motion is 90 degrees, the sine of 90 degrees equals 1. So at this third point, at 90 degrees, we will induce V max. Now, as I continue around the circle and get to this point, again, my angle here is 45 degrees. So I'm back to this point and all the way down at the bottom. Again, I'm at 0 degrees. So the induced voltage is at 0. Now, as I start going up through this field, the flux is going this way, and now the motion's going up. So the direction of current and the polarity of voltage has to reverse. So when I get to this point where the angle is 45 degrees, I will generate a negative voltage, which is the max times 0.707. At this point where it's 90 degrees, I'll be down here at negative Vmax, and again at 45 degrees and back to 0. Now, if I connect these dots, notice what sort of waveform I create. And this is, of course, the waveform we saw last week when we talked about alternating current. So if I rotate a conductor through a magnetic field, I will create a sinusoidal waveform. And this is what our friends at Duke Energy do. This is how electricity is generated, by either rotating a conductor through a magnetic field or rotating a magnetic field around the conductor. It doesn't matter which one changes, because all we're required to have is relative motion between the flux and the conductor. So again, electromagnetic induction requires or states that when there's relative motion between flux and a conductor, we will induce a voltage in that conductor. And the factors that affect that induced voltage are, of course, the strength of the magnetic field, the direction of flux, the direction of motion, the rate of motion, and the angle at which the relative motion occurs, the angle between the motion of the conductor and the flux, or the flux and the conductor. And we see how we generate a sinusoidal waveform by rotating a conductor through a magnetic field.